Welcome to this lecture on the principles of ecology. Today, we are going to explore one of the most fascinating concepts in nature, R and K strategies. Have you ever wondered why some animals have thousands of babies while others have only one? By the end of this video, you will understand the evolutionary choices species make to survive and thrive in their unique environments. Let us dive right in. To begin, let us imagine you are given a choice on how to spend $1 million to build a successful business. You could open 10,000 tiny, cheap lemonade stands all over the city. You know most will fail, but you are hoping a few survive the harsh weather and fierce competition. In nature, animals and plants face a very similar choice with their energy and reproduction. Some organisms, like dandelions or frogs, act exactly like these lemonade stands. They produce thousands of offspring with zero parental care, simply hoping a few will survive the odds. Now that we have seen the lemonade stand approach, let us consider the alternative. You could instead build one massive, highly secure luxury restaurant and pour all your money into making sure it succeeds. Other organisms, like elephants or humans, act like this luxury restaurant. They have very few babies, but invest massive amounts of time and energy into raising them and keeping them safe. This fundamental choice in nature between quantity and quality is what ecologists call the R and K selection strategies. Building on our analogy, let us formally define these terms, starting with R strategists. In ecology, the term R strategist refers to species that are adapted to unstable, unpredictable environments, where survival is largely a matter of luck. Because their environment is so chaotic, their best chance of passing on their genes is to maximize their reproductive rate. They produce as many offspring as physically possible without wasting any energy on parental care. It is a pure numbers game, designed to ensure that at least a tiny fraction of the next generation makes it to adulthood. In stark contrast to the chaotic world of R strategists, let us look at K strategists. These organisms live in stable, predictable environments. However, because the environment is stable, it is also crowded, meaning competition for resources is incredibly fierce. To survive in such a highly competitive space, K strategists produce very few offspring. Instead of numbers, they invest heavily in their physical development, defense mechanisms, and extensive parental care. They are building strong competitors that can hold their ground and secure the limited resources available in their habitat. Understanding these two distinct strategies is not just academic. It is absolutely critical for real-world wildlife conservation. If an endangered K strategist, like a rhinoceros or a panda, experiences a sudden population drop, it is a massive crisis. Because they reproduce so slowly and invest so much in single offspring, it might take decades for their numbers to recover. Conservationists must use this knowledge to design specific long-term protection plans, knowing that K strategists absolutely require prolonged habitat stability to survive and rebuild their populations. While conservation focuses heavily on K strategists, pest management requires us to understand R strategists. If a forest is destroyed by a fire, R strategists, like weeds and insects, will be the first to colonize the empty space because they reproduce rapidly and disperse easily. Similarly, when dealing with agricultural pests like locusts, farmers know they are fighting classic R strategists. These populations can explode in numbers almost overnight when conditions are right. Therefore, managing them requires rapid and aggressive intervention before their exponential growth spirals completely out of control. To truly understand where the names R and K come from, we must look at the mathematical foundation, the logistic growth equation. Conceptually, this formula describes how a population grows over time when limited by environmental resources. Let us break down the symbols. dn over dt represents the rate of change of the population size over time. N is the current number of individuals. The variable R is the intrinsic rate of increase, which is the maximum possible growth rate under perfect conditions. Finally, K is the carrying capacity, the maximum population the environment can sustain. If R increases, the population grows faster. If N approaches K, growth slows down. Now that we have defined the variables in our formula, let us see how they interact physically. Look at the term inside the parentheses, 1 minus n over k. If the population size n increases and gets closer to the carrying capacity k, the fraction n over k gets closer to 1. This makes the entire growth rate slow down to 0. An R strategist is evolutionarily driven to maximize the R value, meaning they want to grow as fast as possible when resources are abundant and N is small. A K strategist, however, is driven to compete successfully when the population N is very close to K, surviving in crowded conditions. Before we move on, let us see this formula in action with a concrete example. Imagine a small pond that has just formed, creating a perfect, empty habitat. We're given an initial population of 100 mosquitoes, an intrinsic growth rate of 0.5 per day, and a carrying capacity of 10,000. We need to find the initial population growth rate. We choose the logistic growth equation because it accounts for environmental limits. We substitute our given values into the equation. Because the population is much smaller than the carrying capacity, the term inside the parentheses is 0.99, very close to 1. Multiplying this out, we get a final answer of 49.5. This means the mosquito population is growing almost at its absolute maximum potential, facing virtually no competition. Now let us contrast the mosquitoes with a K strategist example. We're looking at a stable savanna ecosystem with a current population of 950 elephants. We are given a low intrinsic growth rate of 0.05 per year and a carrying capacity of 1,000. We want to calculate the current growth rate. Again, we use the logistic growth equation. We substitute our values, but notice that the population is very close to the carrying capacity. The fraction shows they are using 95% of available resources. The term inside the parentheses becomes a very small 0.05. Multiplying this out gives a final answer of 2.375. Physically, this means intense competition is forcing the growth rate to slow down dramatically, exactly as K strategists are adapted to handle. Having calculated the growth rates, let us visualize these strategies on a graph. Here, you are looking at a plot of population size on the vertical axis against time on the horizontal axis. The dashed horizontal line represents the carrying capacity, K. Notice the red curve representing the R strategist. It shoots up incredibly fast, overshoots the carrying capacity, and then suffers a catastrophic crash because the environment cannot support those numbers. Now look at the blue curve for the K strategist. It grows much more slowly, following an S shape, and smoothly levels off right at the carrying capacity. This diagram perfectly illustrates how R strategists boom and bust, while K strategists achieve long-term stability. We have covered a lot of ground today, so let us summarize the key takeaways. First, remember that R strategists play a game of numbers, thriving in unpredictable environments by reproducing rapidly and dispersing widely. Second, K strategists play a game of endurance, thriving in stable environments by producing strong, highly competitive offspring that survive near the carrying capacity. Finally, these concepts are not just theories. They are mathematically grounded in the logistic growth equation and are absolutely vital for real-world applications like wildlife conservation and pest control. You now have a solid understanding of how species choose to survive in nature. Great job!